Hello everyone, my name is Chuin-Shan and today I will be presenting this work, the local convexity data-driven identification for materials data, which has been jointly realized by PhD candidate Tung-Huan, Professor Chen, and I. This will be the order of the presentation. First, I will review the distance minimizing data-driven identification method, or DMDDI for short. Then I will introduce our proposed method, the local convexity data-driven identification method, or LCDDI for short. Following that, I will present a problem example which validates the performance of LCDDI, as well as the application of the data-driven identification framework to shape memory alloys. And finally, I will end with concluding remarks and a presentation of our future works. Well, in 2018, Leygue et al. Introduced the DMDDI method, which allows to build material data in a model-free manner. Given a set of mechanical problems subjected to different boundary conditions, we can measure the mechanical strains associated with them using digital image correlation. Then, taking those mechanical strain measurements, the boundary conditions of those mechanical problems, as well as information about the geometry and connectivity of the domain of those problems, we can pass them as inputs to DMDDI. With these inputs, the DMDDI will solve a constraint minimization problem, at the end of which it will output mechanical stresses associated with the mechanical strains we gave it at the beginning, as well as material states obtained through clustering of the mechanical states. And in detail, the procedure of the DMDDI solver is as follows. First, we decide the number of material states that we want from the solver, and based on that, we cluster our mechanical strains into different groups, and we place material strains at the center of them. Then in the second step, we compute material stresses for the material strains that we've computed at the first step. Then in the third step, we update mechanical stresses based on the material states that we've computed in the first and second step. Finally, in the fourth step, we look at the distance between the mechanical states and the material state, and we see if it is necessary to update the mapping between them. If necessary, we do that. And we would repeat that process over and over again until the mechanical states and the material state are stable. And we've implemented that solver, and we found out that the resulting material database tends to be noisy, and we want to improve its quality. To reduce the noise in the generation of material data, we made use of a locally convex reconstruction technique. In DMDDI, each mechanical state is associated to one material state. In LCDDI now, we change that, and each mechanical state instead looks at k closest material states. Then, taking those material states, we project them in a locally convex space where we interpolate an optimal material state. And that optimal material state will better predict the underlying features of the database that we wish to build. And we expect that this interpolation scheme will help in increasing the accuracy of the generated database. Concretely, we implemented the locally convex reconstruction scheme in LCDDI as follows. We kept the general procedure of the DMDDI solver, but we replaced the second step by a new iterative process. As mentioned earlier, in DMDDI, each mechanical state would update its value in relation to the material state that is closest to it. In LCDDI now, we compute an optimal material state for each mechanical state. And after that, we compute new mechanical stresses based on those optimal material states. Then we adjust the material stresses based on the newly computed mechanical stresses. And we would iterate that loop until the material stresses are very stable. And because of this iterative process, we will obtain better material states in the end. To validate the performance of LCDDI, we applied it to the following problem. Well, to obtain our input data, we consider the plate which we subjected to 30 different loading scenarios. And for the database that we want to build, we chose to have 100 material states. And for LCDDI, regarding the number of closest material state that each mechanical state has to look for, we set that number equal to 21. And these are our results. If we compare the mechanical states obtained by LCDDI with the mechanical states obtained by DMDDI, we see that there's a great reduction in the noise that happens using LCDDI. And if we look at the material states as well, below, we've plotted the material states computed by DMDDI in black and the ones computed by LCDDI in green. And we can see that the material state computed by LCDDI are much more closer to our reference line. And then to evaluate the stress values computed by the solvers, we plotted a histogram of the relative errors on the stresses of both the mechanical and the material states. And we obtained those error values by comparing the solver's outputs with values that we would get using a finite element analysis software. And by looking at the distribution of those errors, we can see that we obtain better distributions with LCDDI. For example, if we look at the stress errors for the material states, the distribution given by DMDDI has a mean of 8.24% and a median of 7.36%, while the distribution of errors given by LCDDI has a mean of only 2.82% and a median of 1.78%. And then we chose to directly visualize the mechanical stresses computed by the solvers, and for that we picked one of the loading cases from our input data, and we plotted the distribution of absolute errors for the von Mises stresses computed by each solver. And by looking at the distribution of those errors, we can see that with LCDDI, the errors are on the lower end of the spectrum, which shows the superior performance of LCDDI. Finally, we studied the influence of the number of nearest material neighbors used for interpolation on the final results. And for that, we define global errors on the mechanical and material stresses as shown on the left. And by looking at the error plot, we can make two main observations. First, if the number of nearest neighbors is equal to 1, LCDD reduces to DMDDI, which goes without saying, since each mechanical state is only looking at one closest material state for its interpolation. And as the number of nearest neighbors increases, we can see that the error decreases as well. And that means that the greater the number of material states that LCDDI can use for interpolation, the better its performance. Now, for the application of the data-driven identification framework, we did an experiment on a single crystal shape memory alloy. And first, using digital image correlation, we obtained the evolution of the strain field in the specimen during both loading and unloading. In addition to that, we've drawn different plots of the average stress strain response of the specimen for different loading and unloading scenarios. However, if we would like to locally observe the stress distribution in the shape memory alloy, or the relationship between phase transformations and the dissipation of energy at the local level in that shape memory alloy, we would not be able to do that with digital image correlation. And for that, we will need the data-driven identification framework. Then, using the data-driven identification framework, we can obtain stress fields associated with the strain fields measured through digital image correlation. Given that now we have full field data for both stress and strain, we can compute Martensitic volume fractions for the entire field of the shape memory alloy. Here, C denotes the Martensitic volume fraction, where if C is equal to 0, then that means a fully austenite phase. And while C being equal to 1 means a fully Martensite phase. During the loading process, we can observe two bands of Martensitic phase transformation progressively forming in our specimen, one in the horizontal direction and another in an oblique direction. And then as we unloaded our specimen, they progressively disappear. Now, regarding the accumulation of dissipation energy, we can globally estimate it by integrating over the closed loop formed by the average stress strain response. But given that now we've obtained full phase stress data through the data-driven identification framework, we can also locally look at the distribution of that energy. And on the lower right side of the slide, we show a few snapshots of the dissipation energy during unloading. Now we can look at the relationship between the Martensitic phase transformation and energy dissipation. We first plot side by side the maximum Martensitic volume fraction throughout the shape memory alloy and the distribution of dissipation energy for the complete loading unloading cycles. And by comparing these two figures, we can see that first, the energy dissipation is inhomogeneous. For different regions, we have different levels of energy dissipation. And second, the majority of that energy dissipation is happening in the Martensitic region, which is the red part in our plot of the Martensitic volume fractions. And finally, we plot the incremental changes in Martensitic volume fractions as well as the incremental changes in energy as the unloading process occurs. And we can observe that the dissipation energy occurs mainly in the interfacial region of the Martensite to austenite transformation. And those observations, we've been able to make them only because we've combined digital image correlation with the data-driven identification framework. And using digital image correlation alone, we would not have been able to reach those conclusions. To conclude, we've seen that LCDDI is a generalization of DMDDI, where once we set the number of closest material states that are used for interpolation to 1, both solvers are equal. And we've also seen that the use of locally convex reconstruction in LCDI leads to the computation of mechanical and material states that are more accurate. And finally, by combining digital image correlation with data-driven identification, we've been able to closely observe energy dissipation in a shape memory alloy specimen. Now, regarding our research directions, as of now we've used LCDDI to check databases for elastic materials. In the future, we plan to extend it to plasticity and to multi-scale problems as well. And that marks the end of my presentation for today, and thanks for your attention.